Bismillahirrahmanirrahim. Assalamu alaikum, dear student. My name is Dr. Muhammad Adnan Asgar, and today we are going to discuss the last topic of molecular symmetries. The topic of our discussion is applications of symmetry vibrational spectroscopy. In this lecture, we will study about some of the important applications of symmetry that we have studied already. We know that in our previous lecture, uh, there are different molecules which exhibits different type of molecular geometries, and the based on the structure and three-dimensional structure of different molecules, we can classify these molecules, either they may be the organic one or inorganic one, into different point groups. Before going to study point group, we already studied different symmetry elements that may be present in any kind of molecules. So I would like to just recall the different symmetry elements that we have studied so far. We have studied about the identity, we have studied about the plane of symmetry, center of symmetry or inversion center, which was denoted with I, and principal axis of rotation and improper rotation. We have studied five type of symmetry elements that may be present in a molecule. These five symmetry elements may be present in a single molecule, or some molecule may possesses one, two, or three types of symmetry elements. So the based on these symmetry elements, we can assign a single point group to any specific molecule. This would be quite helpful. The point group might be quite helpful for the direct understanding of different properties associated to that particular molecule. Now let's talk about the some of the applications of symmetry. We have seen how the three-dimensional structure of a molecule determines its symmetry. The symmetry of a molecule in turn will determine its spectroscopy. Spectroscopy is actually deals with the interaction of electromagnetic waves with the charged particles of matter. The process of absorption of electromagnetic radiation occurs when a photon is resonant with the difference between the ground state energy level and any of the quantized excited state energy levels. The resonant with or has the same energy as the difference between the ground state energy level and any of the quantized excited state energy levels. That is actually the case that we have studied already in electronic transitions, which we observed by using Bohr model of atom in our previous classes. Emission is the opposite process where a photon is emitted as a result of a transition from a high lying energy level to some lower lying energy level. This is the concept which is quite important about the emission. We know that emission is the opposite process where a photon is emitted as a result of a transition from a high lying energy level to some low lying energy level. While the emissions that gave rise to the line spectrum of hydrogen involved transitions between electronic energy levels, the spectra of molecules is complicated by the motions of atoms in molecules. Each atom in a molecule can have 3 degree of freedoms, which is actually correspond with the motion along the 3 Cartesian axes, so that every molecule has a total of 3 n degrees of freedom, where n is the number of atoms in the molecule. In general, there are 3 types of molecular motions, that is the translational motion, rotational motion, and vibrational motion. The energy levels for each type of molecular motion are quantized. Trans- Translation occurs when the molecule is moving through space and it has components along the x, y, and z axis, so that there are always 3 degrees of translational freedom in any given molecule. The translational energy levels are small and so closely spaced to each other that translational motion can be approximated as a continuum or will be treated as such. Rotational motion occurs when the molecule is rotating or spinning around one of the 3 Cartesian axes. Therefore, there are 3 degrees of rotation. There are 3 degrees of rotational freedom for any non-linear molecule. Linear molecule have only 2 degrees of rotation, because rotation around C infinity axis does not change the state of the molecule, and we already studied about the rotation and rotational axis in detail in our previous lectures. So from this statement that I have delivered to you is actually the rotational motion occurs when the molecule is rotating or spinning around one of the 3 Cartesian axes. Therefore, there are 3 degrees of rotational freedom for any non-linear molecule, while linear molecules have only 2 degrees of rotational freedom, because rotation around C infinity axis does not change the state of the molecule. The spacing between rotational energy levels is typically on the order of 1 centimeter cube, 1 per centimeter cube, and occurs in the microwave region of the electromagnetic spectrum. Lastly, vibrational motion involves changes in the position of the nuclei in molecules, which in turn affects the equilibrium bond lengths and bond angles. By subtraction, there are either 3n minus 5 or 3n minus 6 degrees of vibrational freedom, depending on whether the molecule is linear or non-linear. Vibrational absorptions occur in the infrared region of the electromagnetic spectrum. The different types of energy levels in molecules are actually superimposed on one another and is shown in this diagram. This section actually focuses exclusively on the vibrational spectra of molecules, although the principles developed can also be applied to the rotational and electronic spectra. Vibrational spectroscopy confines itself to that narrow region of electromagnetic spectrum where the absorption of a photon has sufficient energy to cause the nuclei of the excited molecule to vibrate. Vibrational spectroscopy confines itself to that narrow region of the electromagnetic spectrum where the absorption of photon has sufficient energy to cause the nuclei of the excited molecules to vibrate. For all practical purposes, this actually implies a wavelength in the range of 2.5 to 50 micrometer, or we can set that 200 to 4000 per cubic centimeter per centimeter in wave numbers, with the corresponding energies of 2.4 to 48 kilojoule per mole. Although it might seem natural to assume that vibrations in the molecules involve completely random gyrations of all atoms in the molecule, the actual vibrational motions of the atoms are always a superposition or sometimes the linear combination of certain fundamental vibrations which may be known as the normal modes of vibration. As discussed previously, there are a total of 3n minus 6 or 3n minus 5 if the molecule is linear. So the normal modes of vibration are actually 3n minus 6 for the non-linear, while 3n minus 6 for the linear molecules. And it is different types and symmetries of these normal modes with which we shall be concerned. Each normal mode of vibration occurs at one of the natural frequencies of the molecule in much the same way as a turning fork vibrates at a natural frequency. A more rigorous definition is that a normal mode of vibration in is one in which each atom is displaced from its equilibrium position by an amount that corresponds to its maximum amplitude, and that when they are allowed to relax, they will all undergo a motion at the same frequency so that they will simultaneously pass through the equilibrium configuration. So, a diatomic molecule will have only a single vibrational mode, and it will be a stretching mode that lies along the internuclear axis, that was actually shown in this figure 2. One can consider the two nuclei in the AX bond to be attracted by an imaginary spring that allows them to simultaneously stretch to their maximum amplitude, pass back through their equilibrium bond length, and then contract to some minimum distance in sync with one another. This stretching motion will occur along what we will define as the normal coordinate q. The normal coordinate is defined as some internal coordinate in the molecule along which the progress of the normal mode of vibration can be observed. The resulting vibrational quantum levels for harmonic oscillators are actually shown in this diagram. Notice that the molecule has a 0 point energy even at 0 Kelvin, and that the vibrational levels are evenly spaced. In reality, most molecules, even diatomic ones, do not behave harmonically. At very large values of Q, the restoring force decreases and the molecule is able to dissociate. Therefore, an asymmetrical potential energy curve given by a Morse potential is often used to calculate the quantum mechanical energy levels for molecular vibrations, and which are shown in this diagram. It is actually a comparison of the Morse potential, which is in blue color, and the harmonic oscillator potential in green color, showing the effects of an harmonicity of the potential energy curve where the rise path of the well. The Morse potential is largely a modification of the harmonic oscillator model that adds an empirical correction for the curvature at the bottom of the potential energy well, where dE is the well depth defined in this diagram, and the beta is actually simply a measure of the curvature. The resulting energy levels, where omega E has merely the same value as omega, and the second term is only a small correction of the first one. Now let's talk about the selection rules for IR and Raman active vibrational modes. There are three commonly used experimental techniques for the determination of the vibrational frequencies of the molecules, which is IR, Raman, and resonance Raman spectroscopies. The three techniques differ by a manner in which the quantum mechanical vibrational spacing in molecules are measured. Thus, each technique has its own set of selection rules, or the rules for which transitions will be spectroscopically observed. The selection rules for electronic and vibrational transitions are derived from the time dependent form of Schrödinger equation by a consideration of the way in which the oscillating electric field of light wave act as a dipole moment component of the molecule. Just as the motion of a traveling wave across a body of water will cause a floating cork on the oscillate frequency vertically in harmonic motion as the wave crests and pass by the cork, so it too the electrons in molecule will oscillate in as the electromagnetic field passes through the molecule. In this lecture we will focus mainly on only on the electric component of the electromagnetic wave. The probability of a transition between two stationary states, such as quantized energy levels that we have seen in previous diagrams, will increase as the energy of the light wave approaches that of the energy difference between two of the molecules' fixed energy levels. The absorption of light is therefore a resonance process that actually depends on the nuclear and electronic coordinates of the molecule. Because the electric field component of the electromagnetic wave is oscillating in time, we will definitely need to use the time dependent form of Schrödinger wave equation that we have studied already in our previous classes. So far for this is quite enough, and we will discuss some of the important aspect of the applications of symmetry in our next lecture. Thank you very much.